A Maxwell-Boltzmann distribution curve is simply a curve that relates the fraction of particles versus their speed. So down here in the bottom, we have speed on our x-axis and fraction of particles on our y-axis. So we can see that wherever this curve is the highest is where we have the highest fraction of our particles. And all that really means is that there are more particles traveling at this speed than there are particles traveling at this speed or this speed, because here in the middle, the curve is the tallest, so the highest fraction of particles are possessing this speed. So what you should get out of this is where the peak is the highest could be considered the average speed of these particles. And if you think about it, if this is at the same, if all these particles are at the same temperature, they will be moving collectively with an average speed. Some of them will be going faster, some of them will be going slower, but the majority of them will be traveling with this average speed. If you were to pick a point maybe right here, for example, where the speed is increased, so these particles are going faster, since the peak is not, or the graph is not as tall there, a smaller fraction of particles are traveling that quickly. Similarly over here, you have a small fraction of the particles that are not moving very quickly at all. But primarily what you need to get out of this is that where the peak is the tallest is the average speed of that particular particle. So let's consider a Boltzmann curve that has two curves on it. Before we can really dig deep into this, let's refresh on the fact that kinetic energy is equal to 1/2 times the mass times the velocity squared. So, if this sample of hydrogen and helium are at the same temperature, that means they will have the same kinetic energy, because temperature and kinetic energy are essentially the same thing. So if both hydrogen and helium are at the same temperature, they possess the same kinetic energy. So instead, let's think about now the molar masses of these two. Hydrogen gas, which is H2, has a molar mass of basically 2 grams per mole, and helium has a molar mass of basically 4 grams per mole. If you think about the math involved here, as you consider the kinetic energy between the two, which has to be the same because they're at the same temperature, to make these be equal, if I were to increase the mass of one, mathematically I would have to decrease the volume, or the velocity rather, of that same particle. Increasing the mass means I have to decrease the velocity in order to maintain that same kinetic energy. With that being said, it becomes clear that more massive particles move slower at the same temperature. The more massive particles will move slower at the same temperature when compared to a smaller particle. So back up to this curve. We've got a solid line and we've got a dashed line, and I want to know which particle is which. So if we look at the peak of the solid line, right here is our average, and the average particles here are moving with this speed, just where this red line meets speed on the x-axis. If I consider the dashed line, so this dashed line, here's the peak of it, so there's my average. The average particle of the dashed line are moving at this speed right here, which is less than this speed right here. That means that on average, the blue particles, or the dashed line, is moving slower than the solid line. And now since we have a key up here, we can see that the solid line is diatomic hydrogen, the dashed line is helium, and we can conclude that the solid hydrogen line is moving on average at a greater speed than the dashed helium line, which fits our description down here. The larger particles should be moving on average more slowly if the temperature is the same. So one more example, we have another Maxwell-Boltzmann distribution curve, and this one shows the curve of diatomic nitrogen. Now in red, I want to draw the curve for diatomic oxygen at the same temperature. So nitrogen has a molar mass of 14, but there's two of them, so a molar mass of 28 grams per mole, whereas oxygen has a molar mass of 16, but times 2 of 32 grams per mole. Since these are at the same temperature and oxygen has a larger molar mass, I would expect its average velocity of its particles to be less than the average velocity of nitrogen's particles. So my curve needs to feature a peak that is to the left of the peak of nitrogen. So it would look something like maybe this. That's not great. I'd like to redo that. Let's make it more clear that that peak is to the left of this peak. Something like that. Showing that on average, those oxygen particles are moving more slowly than the nitrogen because the oxygen particles are more massive than the nitrogen particles. And as we said, in order to maintain that kinetic energy, or to maintain that temperature, if you will, if the mass of one increases, its velocity must decrease in order to maintain that proportion.